have the whole weekend to prepare for the quiz. All right, so I brought a few problems. They're obviously not the quiz problems, though some of them are supposed to be similar. What I have here might not be what you have on the quiz because we might drop quiz problems, or because some of them are just meant to make you think and not to give you away the solutions to the quiz. Now, before we get started on this, do you guys have any burning questions or any concepts that you want covered? Based on that, I'll select which problems we do. Yes?
Hey, this actually relates not too much to the piece that if you're looking at like the time complexity to like fill in, I don't know, maybe transfer something from one table to another, do you consider, if it takes a lot more time, I would assume, to move the actual item to the new table than it does just to look at your point and be like, oh, there's nothing there, right? So if you're just going to look through an empty table of size M, like the time to look through that empty table, I'm assuming is much less than the time to actually move an item. Like,
so you're saying we have a
some table.
M things here.
Yes.
Some might be nil, right?
Yes.
And some might have stuff in them.
Yeah.
And you're going to resize that to presumably 2 times M.
Yes.
And the way you do that is you're going to move the elements presumably by rehashing them, right?
Yes.
Okay, so these elements, at least when we use Python, we don't really store big elements anywhere. If you have a big object, we always work with references to that object. So you remember the address where that object lies in memory. And since the memory is finite and small, addresses are all from 0 to a small number, so they're constant. So what you have here is not a big object, it's the address of the big object. So moving is always constant time.
But what about like just looking at, what I'm saying is like if you had to move, like say that the table is completely full versus a completely empty table, it would take more time to move everything out of the full table than it does just to look at the empty table, right?
Okay, so let's see. So writing something here is order 1 time, right?
Yeah.
So moving is order 1 time. Moving one element is order 1 time.
Yes.
What's accessing an element in a table? In a list. You have a Python list. What's the cost of doing an index access?
It's also order 1, right?
Okay. So order 1 index, order 1 move. Suppose you have an empty table. How many indices do you do? How many times do you index?
Well, you look at each one. So it's order 1 times filling the table, right?
M, yeah.
Yeah.
Okay. So if the table is empty, you have order M indices and 0 moves, right? Total running time, order M. If you have a full table, how many indices? How many times do you index in the table?
Still order M.
Okay. How many times do you move stuff?
Order M.
Okay. Total running time?
It's order 2M, which is order M. So it's, I mean, like.
So it doesn't matter whether the table is full or empty.
Okay. Okay. Just wanted to confirm that.
And this is how you do that.
Okay.
Okay. Cool. Thanks. Any other questions? Okay, then we will go over problems in the order in which I like them, which is easiest to hardest, so that I don't have to explain the hard ones. Okay, warm-up problem 1. So you have this recursion and you have to solve it. And you get a hint that n to the power of 1 over log n is 2, which is theta 1. So based on the hint, you can see that it's going to involve some math. It's going to get a bit ugly. So how do we solve recursions? 2 methods. What are they? Okay, substitution formally, but yeah, basically you expand this guy over and over again, and recursion trees. Okay, which one do you guys want to do for this? If you only have one t here, anything works, because you can keep expanding it, and that works. So we can do either method. Which one do you guys want to go over? Tree. Okay. So we start with the first node. The size of the problem is n. What's the cost inside here? Okay. So this creates one subproblem. What's the size? Okay. Square root of n equals n. You solved it already, right? What's the cost? Do people remember this? Is anyone confused about what's going on here? Okay, so two terms. Something involving t and something not involving t. The thing involving t is what we want to get rid of. When we draw a recursion tree, whatever is in here goes inside here. And this tells me how this number relates to this number. So when I go from one level to the next level, this is the transformation. N becomes square root of n. So the transformation here is the same as the transformation here. Okay. What's next? Okay. Cost? Okay. Do we need to do one more, or do people see the pattern? Silence means one more. If you guys don't speak, we're going to go slow. What's here? What's here? Okay. Let's hope everyone saw the pattern, and suppose we've done this for L levels, so we're at the bottom. What should the cost be at the bottom? Sorry, so the cost is, sorry, we don't start with the cost. What should the size of the problem be at the bottom?
N to the 1 function in I.
Okay. Let's say that this is level h, where h is the height of the tree. Over n? Yeah. Okay, so we'd want something that looks like what?
If the recursion tree is height I, it is n to the 1 over 2 to the I, but 2 to the I should equal n, or approximately n.
Why? I like that, but why?
Because if you have,
so
you need to go down until you're only looking at one element, and that would be 1/n of the problem.
Okay, so we want this guy to look like 1. In fact, it doesn't exactly have to look like 1, but what's the advantage if we manage to get this guy to look like 1? We have a recursion. We don't have a base case here, right? A reasonable base case is t of 1 is theta 1. Whatever function that is, if you evaluate it at 1, you're going to get a constant. So you can say that, right? Now, at the same time, I can say that for any constant c, t of c is theta of 1. So if I take this constant here, which happens to be 2, but let's not worry about that. If I take this guy here, I can put it in here. And I know that this guy here equals this guy here. So if I can make this guy here look like this guy here, then I'm done. Make sense? If it makes sense, everyone should nod so that I know and I can go forward. Or smile or something. So this should look like 1. So this is order 1, if not 1. Let's make it order 1, because it's 2 in this case. So what's the cost here? 1. Everything inside the bubbles is order of already, so I don't need to write an order of. Okay, what do we do next? Okay, you're skipping one step. So when we have a tree, that's exactly what you do when you have the substitution method. You're going to get to something and you need to solve the equation. But for the tree, there are 2 steps. So we need to add up all the costs here, and that's the total cost here. In order to do that, first, we sum up over each level. And in this case, it's really simple because there's only 1 node per level. But if you have multiple nodes per level, you have to sum up for each level. And then you have to do a big sum. What's the sum for this level? 1. Come on, guys. You're scaring me.
1. Oh, 1.
Excellent. So the only thing that I'm missing is to know how many levels I have, because the sum is going to be order h, whatever h is. How do we do that? N to the 1 over 2 to the power of h has to equal this guy. Right?
Why would it equal that guy? I mean, we know it's less than that guy, but we don't know it equals.
So we have to make it equal because we can only stop when we get to the base case. So we have to expand the recursion tree until we get to a base case, and then we stop. And this is our base case.
Yes.
Because this is what the problem says should be our base case.
But
Right, that hint.
N to the 1 over 2 to the h is not. Yeah. Yeah. No. I mean, it's not equal to n to the 1 over log n.
Well, we can set h to be whatever we want.
Oh, I
H is
see.
the height of the tree. So we don't know what it is. We have to find out what it is.
Okay, so then say 2 to the h is equal to log n. If you wanted to make it look like that.
Okay, let me write down the equation to make sure you're right. You're probably right because you're thinking faster than me, but let me not embarrass myself and do this the right way. So this equals, okay, so you said 2 to the h is log n, right? Looks about right. So what's h? All right. Log n. So T of n is order h. We got this from here. T of n is order h is order of log n. Math people drowning, right? Okay, any questions about this? Yes?
The first line on the right?
This?
Yeah, is that your base? Wait, what is that?
So we got a hint with a problem that said n to the power of 1 over log n is 2, which is order 1.
Okay.
So for the base case, we always want them to look like this. If we don't get a base case, we write our own base case, which is if you plug in a constant, you're going to get a constant. And since we're told that this guy is a constant, that's a pretty good hint that we want to get to it. Okay, let's see how we're doing on time. Good. All right, so ready to move on to the next problem? Okay, let's do a fun one. Some people might remember it from elementary school, but this time we're going to look at it with a 6046 eyes. So suppose you have n coins, gold coins. One of them is fake. The fake one is super light because it's not real gold. It's something that looks like gold. And we have a scale. And the scale is super accurate. It can weigh any coins on either side and tell us which side is heavier. Perfect accuracy, no need to worry about errors. I want to find out which coin is the bad coin. What is the minimum number of experiments I have to do? So there is a strategy, and we can worry about that later. But using 6006, what is the minimum number of experiments I have to do? Not quite. So this is what you think it is, and you can do log n with binary search, right? So the problem with binary search is if I put half of my coins on the left, half of my coins on the right, one side is going to be heavier, right? So the answers are going to be this or this, but I never get this. So I only get one bit of information instead of getting one trit. A trit is a base 3 digit. How many bits of information in a trit?
1.5.
Roughly.
Log
It's
2 or log 3.
log 3, and we know that it's base 2 because that's what we use in CS. So we're discarding a fractional bit of information if we're not allowing for this to happen. So anyone want to try something else? And we have to prove this, by the way. We have to prove the minimum that we come up with.
Or you could just do it coin by coin, but that would take
Wait,
longer.
Well, that's n. That's worse.
I would like log base 4 then.
Okay.
Explain to me why we can't just do binary search.
So we can, but it's definitely going to give us the correct answer, right?
Okay.
But it's not the minimum number of weighings because we're discarding a possible answer. So if you do binary search, you will never get that the two sides are equal. Log base 3 would be better because we have 3 choices all the time. Now let's prove that. So the right answer happens to be log base 3 of n. Let's see how we would get it aside from guessing.
So you divide it into thirds and compare 1/3 and 1/3, and if they're equal, then the light one is in the other third.
Yeah.
And if they're not, then it's the light one. And you just keep dividing by 3.
Wait, what if?
Okay, so that's the strategy. What if I don't know the strategy? How do I do this without knowing the strategy?
Wait, what if the number of coins is divisible with
Math people.
Yeah, but then how do you? Okay, never mind.
Wait,
Just take the 2
pick,
extra
like, equal
coins and
groups.
toss them, and if they're not, then put the 2 away.
So if it's not divisible by 3, you add fake coins that are good, and I mean you use good coins. But we're not worried about the strategy. I want us to think of a lower bound. So this is a lower bound for an algorithm, right? You cannot do better than log 3n experiments. Does the word lower bound ring any bells? Is there any lecture where we talked about lower bounds? So if you sort and you're using a comparison model, what's the best you can do? And log n. Good. So sorting using CMP, the comparison model is n log n. How did we prove that? One word. Well, 2 words. Decision trees. Does anyone remember what decision trees are? One person.
Okay, it's just a comparison thing, right? Or you're like, oh, is it greater, is it less, or is there some sort of question you're asking about each key?
Okay, cool. So let's go over that a little bit. So no matter what your algorithm is, it's going to weigh some coins, and it's going to get an answer from the scale. And then based on that, it's going to weigh some other coins and get some answer from the scale. And it will do some experiments, and then it will give you an answer. So if you draw a decision tree, it would look like this. First, we start with 0 information. We weigh some coins. Based on that, we have 3 possible answers. Smaller, equal, greater. Now, if we're here, we're going to do another experiment. 3 possible answers. if we're here, another experiment, 3 possible answers. If we're here, another experiment, 3 possible answers. Say we do a third experiment. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then suppose we stop. If we stop, we have to give an answer. So this is an answer, this is an answer, this is an answer, 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 answer. So how many answers do I have at the bottom if I have 3 levels? So here I have 3 experiments, so 3 levels in the decision tree. How many answers? 3 to the third, because I start 3 at the first level, 9 at the second, 27 at the third. Each time I multiply by 3. So if I do 3 weighings, I can give at most 27 answers. If I have more than 27 coins, I can't possibly decide which one is bad. Because if I have 30 coins, then I need to be able to give out 30 answers. My algorithm has to have a place where it says the bad coin is coin 1, coin 2, coin 3, all the way to coin 30. Here I only have 27 possible answers. So this isn't going to cut it for 30 coins. I'll need to do one more comparison so that I have a deeper tree. So suppose I have age comparisons instead. How many leaves? So how many possible answers?
Age just like
Almost.
3 to the age.
3 to the age. So 3 multiplied by 3 multiplied by 3 multiplied by 3 h times. So 3 to the h. It's no longer equal to 27. So 3 to the h is the number of possible answers. This has to be bigger or equal to n. Otherwise, the algorithm is incorrect. So what can we say about h? So we did all this without even thinking of what an algorithm would look like, right? This works for any algorithm. No matter how smart you are, no matter how much math you know, your algorithm is going to be bound by this. So the fact that the answer looks like this gives you some intuition for how to solve the problem. If you want to solve the problem now and figure out the strategy, you know that you have a 3 here. So if you divide into 2 every time, you're not going to get to the right limit. So first you do this, you get a lower bound, and then you use your intuition to figure out what the lower bound means. And in this case, it would mean the strategy that we heard earlier. You have to divide into 3 every time and then figure out what you do based on the comparison. So your answer works perfectly once we have this. And also once we have this, you know that your answer is correct because it's optimal. You can't do better than that. Okay, any questions on decision trees? So lower bounds are a boring topic in general, right? They tell you what you can't do. They don't tell you anything useful about what you can do. But in some cases, being able to reason about a lower bound gives you a hint of the solution. Okay, new problem. So suppose we have a 2D map. There's a hill, and you take a satellite picture of it at night, and you get a picture with bright pixels and not bright pixels. So there are numbers showing how bright your pixels are. 1, 2, 1, 2, 3, 0, 0. I'm going to draw out an example so we can use our intuition. 0, 0. So suppose this is our map. It's W times H. So W of what these are, I think they're columns, and H of the other ones. And you want to find a certain picture inside it. You want to see how many times does a certain pattern show up. Say the pattern is small w times small h, and it looks like this. But this will be the input to your problem, so the pattern might be different. You can't hard code this in. And this is useful. This problem is called the bunker hill problem. So this is a hill, and this is a bunker. You take a picture of the hill. You want to know where the bunkers are so you can bomb them at night, so then you can attack the place. Thank you. I'll take that as a compliment. So naive way of solving this.
I mean, you could just go through each row and then look for a match for the first row.
Yep.
And then
So
if you
is this a match, right? That's
well,
what
yeah,
you're saying.
I mean, we can see that's a match.
Is this a match? Is this a match? Yeah, by the way, this is a match. This is not 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 a match. Now we go down here. This is not a match. This is not a match. This is not a match, so on and so forth.
That's what I was suggesting. That's a good idea.
So this is, maybe you're suggesting something smarter, and I don't want to let you do something smarter so that we look at the brute force approach first.
I mean, like I was just saying, take like the first row of your bunker and then like compare it to other rows, and once you hit that, then check and see if the rest of
Yeah, that's a bit smarter. So that's harder to reason about. Let's take this one and know figure out the running time of it.
Does that mean even if you know it's not a match, you keep checking all 9 of them?
Yeah. Say in the worst case, you only find out it's not a match all the way at the end.
Wait, are you trying to look for all matches or just one?
All matches.
So you're limited to n squared time almost no matter what, right? You have
Okay.
a small bunker in a large field, you have to hit the small bunker every time.
Are you going to solve the problem for me?
Are we trying to find the most efficient algorithm?
No, we're trying to find out the running time for the dumb algorithm first.
Oh, okay.
Humor me and let's solve this first, and then let's get to the efficient algorithm.
Big
Okay?
W minus small w plus 1 times big H minus small h plus 1.
Where's your plus one from?
Okay.
Just like mark cases.
So it's WH.
Yeah.
Well, there's something missing here. So this is how many positions I have that I have to look at, right? How much time does it take to compare the small images? All right. Well, this is smaller than WH, which is the input size. So it's scary if you have an algorithm that runs faster than the input size, because it means you're not looking at all the input. Okay, so this is definitely bigger than the input size once we add the W times H here. Don't forget this guy. So this is the naive algorithm. And if we discard the small order factors, we get that this is order of WH, WH. How can you do better? You have the answer, right? Let's let everyone else think for like a minute, and then you can give me the answer if you want, or someone else can give me the answer. I guess you should, because you thought of it first. Any ideas? So you're thinking about the input size, right? Someone was thinking about the input size. So the input size is W times H, right? So if I have an algorithm that's W times H, that's optimal, because it has to look at all the input. Well, we're going to have an algorithm that's W times H. So with that out of the way, does that inspire anyone as to what the solution is?
Do that thing that I was saying. Just take like the first row, but then you still have a W term. So
Yeah, so let's make it better. It is the correct intuition. Now try to use a trick we learned in lecture to make that faster. Okay, so we could use the top left corner, and if the top left corner doesn't match, then we don't have to check for matches. So this works for reasonably random data, right? As long as we don't have a lot of false positives, we're going to run fast. Now, if the top corner of this one, if the map has a lot of ones and then some twos sprinkled all over it, most of the time we'll have to go through the whole image. So we're going to have a lot of false positives. How do we make our false positive rate go down?
Looks kind of like a rolling hash problem.
Looks like a rolling hash problem, exactly. So let's see if we can use rolling hashes.
But then you still have that lowercase w term, though.
How do we get rid of it? Sorry?
Oh wait, well, it would be w. I mean, like the running time, if we were just going through one row, it would be big W minus little w. And then times,
So where's your rolling hash?
oh, well, you mean like you start with, yeah, the first row. Oh, I guess you can use the entire thing as a hash, too. Like, that kind of works.
So we'd want a hash for the whole thing, right? So instead of using this as the
row,
hash,
yeah.
we want a smarter hash.
Yes, the entire thing. And then as you like move to the right, you can add those and subtract them. Well, that's simple. And compare that with the hash up here.
Okay, so we'd have a rolling hash that say has everything in here. And then as I move to the right, I add these guys and I remove these guys, right? So this is W times H, big W times big H, roughly, times small h, because I have to add, every time I move to the right, I have to do order H work. Right, so I'm down from this thing to order of W, H, H. So it's better. It's one step forward. Now let's make this even faster. What if I could do this in order 1 instead of order H? How would I do this in order 1?
You have to compress all the rows,
Okay.
and then take the hash of like each
So
column.
how would we compress them?
Take the hash of the column. Like,
So you want to compress the rows?
yes,
Wait,
you
are
divide
these
it.
rows?
You divide
Okay,
it. I don't think it's
let's not compress the rows.
Yeah. I mean, oh, I guess you could. I mean, you could take just your bunker and then figure out the hashes of the 3 columns, and just run through like that. But I mean, you still have to access each of those items. So I don't really see how that's faster. I mean, I guess it's less though. It's less. Maybe it's only 1.
No,
Well,
you
I
have.
wanna-
Sleep last night.
So do you want to like hash each little column with height h?
Okay.
As a height low h.
Okay, so we're going to hash all these guys, right? And then we're going to have hashes for them. And we're going to do the regular robbing carp for the hashes, right? Now what happens when I go down?
Do you want to
Let's do better than recompute everything.
downward on each column?
Yep, rolling hash. So I want to make this faster, so I have big W hashes. They're all little h inside. Here I have to compute them brute force. I can't do anything better. But when I go from here to here, there's only one element going out and one element going in. Same for all these guys. Let's not make the picture uglier than it needs to be. So I have big W rolling hashes. They're vertical rolling hashes. And then the rolling hashes hash columns. So my window, the sliding window that I have, is little W rolling hashes. Each rolling hash is little h in size. So it's a hash of hashes. It's nested hashes. And then when I go down, I only have to roll down each of the rolling hashes by 1. So that's constant time. So to go from here to here, so to slide the window 1 down, I have to roll this hash down, roll this one, this one, this one, this one, this one. And all of them roll down in constant time. So when I'm adding a column to the hash, say I'm here, and I want to go here, I roll down this hash, and I have the answer. So it's order 1. I'm adding it in order 1. Does this make sense? But it's not too bad, right? It's one more.
Do the vertical roll first, right?
Yep.
Okay.
Yes.
Okay.
So to make to have the simplest possible code, you start with big W rolling hashes, do 1D robbing carp, you roll everything down, 1D robbing carp,
Right.
and keep doing that. Okay, what's the running time for this? WH.
Does this one have a space complexity above W then? Because you can store literal
Yep.
hashes?
So my memory requirement went up to 4W. Okay, is everyone happy with this? So it's one of the few cases where an approach for solving a 1D problem generalizes to 2D. In most problems, you have to rethink the whole situation. Okay, let's do a hard problem. Enough with the easy ones. Two lists, roughly size n. They're both sorted. Let me fill them out with random numbers. 5, 13, 22, 43, 56, 72, 81, 86, 87, 2, 3, 7, 9, 15, 19, 24, 28, 32. So I have these lists. Let's be generous and say that all the numbers are different. They're sorted. I want to find the nth number, so the number with rank n, out of both lists. As fast as possible.
Isn't that just the index?
Well, so the thing is, if, for example, n is 1, then it's this.
Yeah.
This is the second number. This is the third. So,
Okay. Sorry, I thought it was
so if you take the lists and you combine them, then I want the result out of that.
Let's do merge sort and say that they're combined, and then it is the index, right?
Okay. Full merge sort and log n? No.
Well, it's already sorted though.
Okay, so what do we do?
Merge, so that's just order management.
So merge. Right?
Merge first n.
Okay. So merge and then index is the first approach, which is order n. Then you say run the merge algorithm, but stop when you get to the little nth element. So that's a little bit better. And we don't have to produce an array, so the space complexity is down to order 1. Right? Okay. Now let's do...
Logarithmic time.
Yep, exactly. This is linear. We have to get to logarithms. How do we get to logarithms?
Do a modified binary search.
Okay.
So, like, what if you had first looked at, actually, I don't know what I'm gonna say.
Okay. Anyone else? So modified binary search. Do you know the full answer, or do you want to start looking at the solution?
I have an idea of
Okay.
what to get.
Let's see how it would work.
Okay, so if we take the n over second element on each, or sorry, the n over second element on each row, the one that is lower, if that's at least the n over second element. And the one that's higher is
So let's say the lists are n1 and n2 to
Yeah.
make this, and they're both order n initially. So this is n2 over 2 if this is small.
that's it. So that's at least the lower one is at least the n over second element, since everything before it is since everything before it is what you call it is less than it. Does that make sense?
Yeah, so this is n over 2 or greater, right? This guy.
So then we know that we also know that it has to be greater than the element above it is at least the nth element, or is it, yeah, at least. Sorry, it's at most the nth element because it's greater than.
So it's at most n1 plus n2 because that's how many you have in total, and you know that the one on the top, you know that these ones are bigger than it, right?
Yep.
But you don't know anything about these ones.
Mm-hmm.
So it's minus n1 over 2, right? So it's at most n1 over 2 plus n2, the top element. Okay.
So then we can take the element halfway between, let's 3/4 of the way through n2 and 1/4 of the way through n1, and just do more useful comparisons. Or is the element someone pick? Yes.
Okay, so you're saying that if, so let's see what happens in each case. So if little n is here, then you divide. So if n is smaller than this, right, then you chop them up here and you've divided the problem into half.
Yep.
You're good. If it's bigger than this other number here, you've chopped the problem up and you're here, you're good.
Yep.
Now, the hard case seems to be when it's in between. So what do we do then?
Wait, aren't those two numbers the same?
If it's between, you take the upper half of the bottom one and the lower half of the upper one, right? If it's between 15 and 43, then you take everything with the upper half of n2, and you take the lower half of n1. Okay?
Yeah, you should always be taking the upper half of one and the lower half of the other. In this case.
Wait, really?
Yeah.
So
Every in list n2, everything less than 15 is 15 is at least the nth over 2 element.
Yeah.
I think we're using
But-
too many n's at the same
Are you
time.
using the little one or the big?
Yeah, I'm sorry. I'm using. We have
So
one
the thing
nth
is-
element in the lists are called n, and this is confusing. Can we rename the nth element to something like m, or some other useful number? The kth element. Okay. So the 15 is at least the kth over 2 element. So it can't be anything on the left half of the.
k over 2? Why k over 2? This list is size n.
Oh, sorry. We didn't. I didn't pick the elements at n over 2. I picked the elements at k over 2.
Okay. So why would I do that?
Wait, that's not the right
K's your rank.
So if
k is.
if n1 is greater than k,
We want the kth element.
Yeah.
then I chop off the end of the list, right? If n2 is bigger than k, then I chop off the end of the list completely, right? If this list is sorted and I want the third element, I know that these are not the answer. No matter what's down here, these are not the answer.
Yeah.
So I know for sure that k is going to be bigger than n1, n2. So instead of going at there, let's go at k over 2, and here let's go for k over 2. So now this one looks a bit nastier. n1 plus n2 minus, oh, it stays what it was before. Okay.
Okay, so on the list where you got the element that was lower, you know that everything to the left of it is less than k over 2, or it's not. It has to be lower than the element number is lower than k over 2. So we're not doing anything to the left of the 15. You can kill that section of the list.
Okay, so we can kill it.
Yep.
But then what's the rank? When I recurse, how am I going to know the rank that I'm looking for?
K minus what you killed.
So,
you can save the
oh, sorry, so you want to kill this guy, right? So you want to kill these numbers.
Mhm.
But here I have k over 2 numbers.
Yep.
And here I have k over 2 numbers. How do I know that it's not somewhere here?
How do you know that what's not somewhere there?
Well, so you compare like 15 and 43, right?
Yeah.
And then you see that 43 is bigger, you see 15 is smaller.
Mhm.
So then you would look at, you would go to, I guess, k over 4 index in N1, right? And like 3k over 4 in N2.
When you recurse, you say that you've killed k over 2 elements, and
I think you can also kill everything to the right of 45 or 43. Whatever.
yes, you can kill everything to the right of 43 since it can't be any of those elements.
So basically, yeah, that would.
And you can kill everything to the left of 15, and then you recurse. You repeat the algorithm again with the lists you didn't kill, except you also put in a term of you've already covered k over 2 elements.
Yeah.
Okay.
That makes sense?
So we want the element with rank k over 4 over these lists.
Yep.
So next time I'm going to have, so I know for sure that what I have is either k over 2 or less than k over 2.
Yeah.
Right, so this is less than k over 2. And then I'm looking for a rank of k over 4. That seems to work. How does the running time look like?
Should be O of log k.
Wait, I think it's log n1 plus n2.
So log k log n1 plus n2. Are these different?
Yes.
If k is 1, the algorithm should only take a runtime of something like, should only recurse once, even if n is 20 million.
Okay, so
But if k is 20 million and the list's lengths are 2 million long, it'll take approximately the list lengths to run.
okay. So what gets reduced is aside from the list size, k gets reduced, right? And k seems to define the input size for the next iteration because I'll have at least k over 2 elements in one of these buckets. So sounds like it should be log k. Okay, now k is k is bigger than n1 and 2. But it should hopefully be smaller than the sum because otherwise why am I doing the problem, right? So this is definitely order of n1 plus n2. So this is a bound, this is a slightly tighter bound. Okay, we have a different solution to the problem, which is all the possible solutions are hard to argue. They all come down to something like this. The one that we have requires you to use, you have 2 indices, and you know that the sum of the indices is k. And you do binary search on the top and adjust the index on the bottom to match, to keep the constraint that the sum of the 2 indices is n. And you can look at that in the notes that we're going to post. Okay, are you guys tired? Do you want to look at one more thing or are we done? Okay, let's try to look at.
No one else said anything.
Okay, let's look at something reasonably easy. Oh no, you guys can read this on your own. I'm not gonna bore you with that. So suppose you have some functions, and we want to order them according to their asymptotic growth rate. Do people remember how to do this from p set 1? So the idea is that you take each function, you simplify it, and then you sort them. So let's have a couple of simple ones and then some hard ones. And we're going to stop in 5 minutes. What's this? Okay. Let's see. N choose 3. What is this? Okay, very good. Why?
Something about chooses like n times n minus 1 times n minus 2.
It's a factorial over n minus k
1 times 2 times 3.
That's k factorial.
So yeah, this comes out to be roughly n cubed. Cool. What do I like? How about n plus log to the 4th of n? Yep. So even if we have a polynomial in a logarithm, it's still dominated by pure n. Now suppose we want to order these guys together with, let's see, which one doesn't look boring at all. N to the log n and 2 to the n. Let's sort them. Which one's the smallest, which one's the biggest? Let's start with the smallest ones because I think that will be easy. So which one's the absolute smallest out of all these guys? Okay. Then cube and 4th. So we have to compare these guys. How do we compare them? N to the power of log n and 2 to the n something.
You can like take the log.
Take the logs. So when we have something confusing with exponentials, take the logs and see what we get. Logs are monotonic, so if you take the logs, you'll have the same relationship afterwards. So log of this is log of n to the power of log n. So it's log n times log n. So it's log 2n. Log of 2 to the n is n. Which one's bigger? All right. Whoops. All right, and we're not going to solve this, but how would you go about solving this guy? What do you do to it? Stirling. Yep. You do Stirling, you go through the numbers and you figure out the answer. And then if you have to do logarithms, use logarithms to figure out where it belongs among these guys.
So this formula is that gross thing that was on the board before we came in here?
So Stirling says that n factorial is ugly 2 pi n over 2 pi n here times n over e to the power of n. So what's this binomial? What's the formula for it? Okay, formula for n choose k. Anyone?
It's n factorial over k factorial times n minus k factorial.
Okay, so in this case, it's n factorial over n over 2 factorial raised to the power of 2, right? And then we chalk through the math and get to some answer. All right? Okay. Have fun.